Hello all and welcome to this video where we start our look into the greater broader topic of polynomials. Now we have already looked at polynomials by looking at quadratics. Quadratic is a type of polynomial. Same with a linear equation. A linear equation is a type of polynomial. Now a polynomial is defined as a function as it says there where p of x is equal to what looks like that really complicated expression. All that is actually saying, if you look at it, is that we have a bunch of x variables, where it's a function of x, that have some other coefficients. Okay? Now, they could be all the same, they could be all different numbers, and each of the x has a power. Okay? Now, the rule for these is n being the power, needs to be a natural number. Okay, and the other rule is that the coefficients need to be real. Okay? So can't be imaginary numbers. So while that may look complex, what that is actually saying is that all it's going to be is maybe 3x squared plus 2x plus 1. And I forgot to say, there may or may not be a constant on the end, that a0. So that 3x squared plus 2x plus 1 is a polynomial. It has different x terms of differing powers. Those powers are natural numbers, so positive integers, and they have some coefficients. Another one might also be 3 on 2x to the power of 4 plus 5x squared minus 9. That is also a polynomial. It has some x terms with whole positive powers, and it has some coefficients, and in this case has a constant on the end. And we can go up to any power we want to. Technically, a polynomial might be 15 on 2x to the 99 minus 3x 66 plus 4x squared. That's a polynomial. Okay? Now, why do we care about polynomials? We care about polynomials because they generally are really handy to describe different real-life situations. We've already looked at linear ones where we have a proportional relationship. We've looked at quadratics where we have maybe a changing relationship. We get to a maximum or a minimum situation. And we'll look at more complex ones in this topic. In particular, we're going to look at polynomials that get up to the power of degree 3. We'll very briefly touch on x to the power of 4. Now, polynomial degree 3, that's called a cubic, and to degree 4 is called a quartic. Okay. The way we can also talk about them is the degree of the polynomial. So the degree of a polynomial is given by the index n of the leading term, and we should say the leading term has the largest power. So in a quadratic, the largest power is 2, so it is degree 2. In a cubic, it has the largest power of 3, it is degree 3, quartic, degree 4, so on and so forth. This x to the 99, that would be have a degree of 99. Now with polynomials, we can always add them. We could add two polynomials together, we can subtract two. So sum is add, difference we can subtract, we can add, we can also multiply them, and when we do that with polynomials, that will always get another polynomial. It will keep its natural number power. A lot of the time with division, we can also divide two polynomials, but it's not always going to stay a polynomial. Sometimes the powers change, that it doesn't hold that relationship here. It doesn't stay like that. So enough about describing polynomials, let's get into start just using some basic form of it. For all these videos, the idea is that when I bring it up, I'll say pause, so that's your opportunity to go through all those questions on that, and then you can unpause and I'll be going through the answers. So here's your opportunity to pause and give it a go. Right here, so the order of polynomials is pretty straightforward. Largest power, so that is n equals 3, so it is of order 3. Find P1 and find P of negative half. That's using that function notation we've already looked at in our next topic. That's pretty much just saying let x equal 1, and over here that's saying let x equal negative half. So P of 1 is equal to 1 cubed minus 3 by 1 squared minus 2 by 1 plus 1. And we get 1 minus 3 minus 2 plus 1. And that gives us negative 5 plus 2 in the end, so that will be negative 3 as our final answer. Key thing to note here is that the squared, unless this bracket is assumed to be being applied to the variable only. So if you see that 3x squared, that's not saying 3 times x all squared, that is saying 3 times by x squared itself. If we wanted the 3 to be squared as well, we would have that bracket, and again the negative sign's outside of it, so it's not impacted by the square, or we could also have that situation. So you just have to be really careful with your signs and not think they're disappearing because the x is being squared. P of negative half, so this is where we're going to have to work a little bit on our fractions, and this time the negative is being substituted directly into the x, so that will be affected by squares and cubes. 3 by negative half squared minus 2 by negative half plus 1. So, just a reminder on index laws, if we have a fraction to whatever power, we can apply that power just to the top and just to the bottom. The nice thing about 1 to any power is still equal to 1. So 1 cubed is 1, 1 to the power of 4 is 1, 1 to the power of 99 is 1, it just stays. Any negative cube, so that's a negative times by a negative, which is turned by positive, which turns to a positive, times by a negative again, so negative times by negative times by negative, that is an actual negative. So we get negative 1 on, so the 1 cubed is 1, the 2 cubed is 8, minus by 3 by negative half squared, so that's a negative times by negative becomes positive 1, the 2 squared is 4, 2 by half is just 1, and the negative times by the negative turns in plus 1, so we get negative 1/8 minus 3/4, taking the 3 inside, plus 2. We want to change all these to a common denominator so we can simplify a fraction, so that's negative 1/8 minus 4. I want to convert to an 8, so times by 2, so I multiply 3 by 2 as well, so I get negative 6/8 plus 2, making on 8 times 8 by 2 is going to give me 16. So I get 16/8, take away the 6 is 10, take away another 1 is 9, so I get 9/8. And there we go. Rightio, very similar sort of thing. Let p of x equal to blah. If p of 2 is equal to 0, find the value of a. So that's pretty much saying when x is equal to 0, y, or we could say p of 2, is also equal to 0. So we get 0 is equal to 2 cubed plus 5 x, not x, 2 squared minus a by 2 minus 20. We get 0 is equal to 8 plus 2 squared is 4 by 5 is 20 minus 2a minus 20, negative 20 and positive 20 cancel, so we're left with 0 is equal to 8 minus 2a, add the 2a to the other side, so we get 2a is equal to 8, so a is equal to 4. Okay. Now it just says find the value of a, so we could stop there. If it then said find what p of x is, you would have to write the full p of x is equal to blah 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 blah, but it doesn't. Okay, let f of x is equal to x cubed minus 2x squared plus x, and g of x is equal to 2 minus 3x. Simplify f of x, take away g of x. So that's just saying take the first polynomial, which in this case is the cubic, and then take away the whole second one. So that's just a matter of collecting like terms. So we are going to get x squared, x cubed, take away 2x squared, and then we have a plus x, take away, so looking at x and the 3x, x take away negative 3x, that's like adding. So we're going to get plus 4x take away 2. And there we go. That's how easy it is to actually add and subtract polynomials. It's just a matter of looking at things that have the same powers, and they're your like terms. Rightio, how are we going for time? 10 minutes, so we need to get going a bit quicker. If we're given enough information, it's possible sometimes to equate coefficients. So just as a reminder, coefficients are the numbers out the front. Now, this is actually going to come up a lot, and it's going to be a way that you'll be told to either expand or something to do with factorizing, and you'll see on the next slide an example. It's either when we're trying to factorize really large polynomials, so cubics and quartics, you'll use this equating thing to help factorize and figure out some unknowns that you might have. In this case, if we're told P of x is equal to Q of x, well, that's the first equation is equal to the second equation. And that means when we look at like terms, we clearly see those are the only two x cubed terms. Those are the only two x squared terms. These are the only linear terms, or x to the power of 1, and then these are the only constants. Okay, so therefore, if we're told P of x and Q of x are equal to each other, they must be the same, we can then say, well, A must be equal to 3 to match. B must be equal to 2 to match. C must be equal to 1 to match. And then D must be equal to 7 to match. So that's all it is equating coefficients. If you have two expressions that have to be equal to each other, then if you collect like terms and match the terms up on the left and the right hand side, the numbers out the front, the coefficients must match if those two things are to be equal. So here's an example. It is known that x cubed minus 7x squared plus 4x plus 12 is equal to x plus 1 in brackets multiplied by that quadratic in brackets, which makes sense because if we have this x, we need to multiply it by an x squared to make this x cubed term. X times by x squared is going to give me x cubed. Okay? And then the rest of it works out from there. We want to find what B and C are. We want to be able to figure out what that is and what that is. So how can we do that? Well, let's expand those brackets on the right hand side and collect like terms. So we get, to do the expansion, we need to multiply everything in the first bracket by everything in the second bracket. So the x is going to be multiplied by that, multiplied by that, and multiplied by that. This is just using what's called the distributive law. And the 1 in the first bracket is also going to be multiplied by that, multiplied by that, multiplied by that. So we get the first bit, we have x times by x squared plus x times by b of x. And I'm just putting this in full just so everyone can see the working, but you can do this much quicker in your own notation. Plus x times by c, and then we also get plus 1 by x squared plus 1 by b of x plus 1 by c. So let's do those multiplications, make it a bit easier. X by x squared is x cubed, obviously. X by b of x is bx squared plus cx plus 1 by x squared is just x squared plus 1 by bx is just bx plus 1 by c is just c. So now we just want to collect our like terms. So let's have a look what we can see. There's only one x cubed term, so that's fine. That's by itself. Change on me. X cubed. We have two x squared terms there and there. So we want to combine those so we can get plus b of x squared plus x squared. And I'll show you how we can take a common factor out in a second. And we also have two linear terms, so power of 1, so we get plus cx plus bx, and then plus c on the end. Last thing we want to do to really help to find b and c by equating coefficients is we have currently 2x squareds. How can we match that to 1x squared? Well, let's take x squared out as the common factor, and what we actually get, if we take that whole thing on the left, we have the x cubed plus, now if I take x squared out as a common factor, well, how do I get the b and then just the 1x squared? Well, that would be b plus 1 times by x squared. So I'm taking x squared out of b, and I'm also taking x squared out of the x squared, so I'm just left with 1. And we can do the same thing for this cx plus bx. I can take x out as the common factor. The only thing is I'm taking the common factor out and actually putting it at the end instead of the front. So if I take x out of cx, well, I get c. I take x out of bx, I get plus b. And then I just get a plus c on the end. So that's those brackets expanded. Now, last thing, now let's find b and c by equating coefficients. Well, this is where it comes down to that idea. What are my x cubed terms? What are my x squared terms? What are my x terms? What are my constants? Well, that's my x squared. That's my x squared up there. So for those coefficients to match, it follows on that -7 here. -7 must be equal to b plus 1. Well, that's obvious from there. Take the 1 away from both sides, we get -8 is equal to b. So that's what b must be equal to. Also, looking at the linear term, we have 4x. We now over here have c plus bx. It's obvious that 4 must be equal to c plus b. So we now know b was -8, so we get 4 is equal to c minus 8. So add the 8 over, we get 12 is equal to c, which we can also check by c is our only constant, 12 is our only constant, so that also matches up that c had to be equal to 12 by looking at the constant on the end. So that's how we can find b and c, by equating coefficients. If we group all our like terms, our x squareds must match up. The one in the original problem was -7. The one that we got was b plus 1, so we solved, we get b. Rightio. Okay, last bit of this, and this is the last bit of the video. We won't need to worry about that last slide. Okay, now how can we write that x cubed, that polynomial of order 3, how can we write this original thing as 3 linear factors? Now, what does linear mean? Well, or linear factors, well, that means something like x minus b. That's a linear factor. It's what is something that it can be divided by or written as a product of 3. Well, it says product of 3 linear factors. So we want to eventually write this as x, well, plus 1. We already know that's linear because it's, and linear means power of 1. We want to write it all in brackets, 3 sets of brackets multiplied together, product, 3, linear, so that means x to the power of 1, somewhere in a bracket. So this x squared plus bx plus c, we want to actually write that as something in brackets, and we need to figure out maybe what it would be as e and f. Now, the hint is obviously factorize the quadratic from that we figured out from part A. That we found here. So we figured out that b was -8 and c is 12. So we could write it as x plus 1, which was the original bit we had. And then we had x squared. B we said was -8, so -8 x. And we also figured out c was 12, so we can write it as plus 12. We can write it. That's the whole point of doing part A and part B, to write it, to expand it, and then figure out what it was equating coefficients. Is we can now write it like this, and now it's written like this. We can just use inspection. So we need 2 numbers that multiply to give us 12 and add to give us -8. So we could use 1 and 12. We could also use 2 and 6. We can use 3 and 4. And we could also use the negative versions of that, -1 and -12, -2, -6, -3, -4. They all multiply to give us +12. Which of those add to give me -8 is that one there. So that's how factorized using inspection. So we get The two numbers in there must be -2 and -6. And that's it. That's that original expression written as a product, because there's technically a little hidden times sign in there, is a product of 3 linear factors. This is linear because it's x to the power 1, x to the power 1, x to the power 1. And that's it. This very last slide is just a shortcut to expand cubics. It's handy to remember. It's not something that I always remember. I just slug it out quickly. Expanding, just write it out long and then expand the first 2 brackets and then expand out the third one. So it does, if you can remember it, it's a great thing to have. It's a great thing to have in your reference book. If you see that you have to expand a cubic, then you just copy that. Really straightforward. But yeah, it's not something I remember for a reference-free test. That's it. That's an introduction to polynomials and the process of creating coefficients. That process of creating coefficients we're going to use heaps later on when we're going to do division of cubics and quartics. So something you really want to wrap your head around. Have any questions, feel free to put it in the comments below or on Google Classroom or email me directly. See you and have a good day.